Hello.
Hey, how you doing?
Good. How are you?
I'm good.
Hey, that's
Uh, what's new?
nothing.
Okay, well,
I wish there's more exciting things to say, but right now it's just
okay, that's fine. Well, we have something new today.
oh, fun.
We're going to do a low impact workout on physics too. And what I mean by low impact is we're not going to look at any problem solving, just the basics. So we can come back to learn how to do some of the problems and questions. So it shouldn't be too bad.
Physics earlier, so
What's that?
I did a little bit of physics earlier, so hopefully I'm a little warmed up.
Good. Oh, that's important. Yeah. Well, let's take a look at something basic since you've looked at physics already. Does this number?
Up, Richard.
What's that?
Don't get your hopes up now, Richard.
Oh, okay. I won't. I won't. But this number over here with the unit coulombs, does this ring a bell?
I saw this one today too.
Okay. Well, this is the charge of an electron. Okay. Now you don't really need to know that, but it would be nice to know it because it makes you feel comfortable.
Yeah.
Yeah. Now I'm going to write another number right next to it. This is positive 1.6 times 10 to the minus 19th.
I'm going to say proton.
Yeah, that's the charge of a proton. Okay. Now, the thing about charges are that if you have opposite charges, they're going to attract. So if we went ahead and we want to put an electron here, and we put a proton here, and we said that this distance between them was going to be something like an R, there's going to be a force on the electron, and there's going to be a force on the proton. And according to Newton, those forces must be equal and opposite. Okay. Now, obviously, if this was two protons, then the forces would be in the opposite direction. But this force was defined by a guy named Coulomb, and it's called Coulomb's law. And this Coulomb here was named after him. So one day there'll be a unit named after you if you do some more work in physics.
I don't think so.
Okay, me neither. Neither one of us is good. We know it's not going to happen. But anyway, so this is called Coulomb's law. And it looks like this. The force is going to be equal to a constant K times one of the charges, which will say Q, and the other charge will say Q, little q, and then this will be R squared. And that's Coulomb's law. And they call this an inverse square law. Do you know why they call this an inverse square law?
Because one goes up and the other one goes down.
Yes, that's the inverse part. And what we're saying is that the force is proportional to 1 over R squared. And that's where the squared part comes in. So that's Coulomb's law. Now, we're not going to do any serious problem solving, but what we could do is we could say, let Q double. Now, we've worked on some of these before. They're called proportionality problems. And let R double. And we want to know how this will affect F.
It becomes.
And the way we did this, if you remember, is we put a number in for Q, and we put a number in for R. And when they double, it's 2. So what do you think is going to happen here?
I put 2 at the top and 2 at the bottom, and then it would be a smaller number because it'd be 1/4.
Okay. Let's work it out, okay? I'm going to work it out the baby way. The baby way to do this is to say F, the new F, over F, the old F.
Oh, it's half.
Yes, yes, is going to be 2 over 2 times 2.
Got it, yeah.
Okay, that's going to be half. Okay, so that's how that works. Now, you may recognize a similarity between Coulomb's law and another inverse square law involving force. Can you tell me what this pertains to?
They're the different masses.
Yeah, this is gravitation. So gravitation is also going to be an inverse square law. In fact, it has the same form. So the things that we did here for force, for Coulomb, we would do the same thing for mass and distance for gravitation. Okay, so that's kind of nice. Now, what I'm going to do here is a very, very minor derivation. You know, if we've got two charges and there's going to be an attraction or repulsion, we have potential energy.
Mm-hmm.
Because potential energy is that kind of energy where if we let it go, it turns into kinetic energy. So this is going to be a very quick derivation. What I'm going to do is I'm going to say F is going to be K QQ over R squared. And I'm going to bring the R, one R up to here. So when I do that, I get F times R, that's force times distance, equals KQQ over R. And it turns out that this is potential energy. Okay, force times distance is energy, and this will be potential energy. So we can derive an equation for the potential energy of these two charges that we have right over here.
Mm-hmm.
Now, if we let the electron and the proton go just before they collided, the kinetic energy would be equal to the potential energy. Because potential energy turns into kinetic energy at that, well, at every point, but at the last point before they collide, that's when they're equal. Does that make sense?
Yeah, and I have a quick question.
Yeah.
Is this formula, because I know I've seen it a lot with the absolute signs, is it the same kind of thing or is it different circumstances where you would use them?
When you say absolute, you're saying absolute in terms of the charges.
Yes.
Yeah. Here's what you can do with that. Ignore the charges in this equation. That's why they're using absolute. And determine the direction of the force by drawing a picture. And if you've got negative and positive, they're going to be coming together. And if you've got positive and positive, or negative and negative, they're going to be repelling.
Gotcha. Okay.
That's why they're doing it. And that's a good practice. It's easier that way. It's confusing the other way for most people. So that's it. Okay. So this is going to be that potential energy here. Now let me ask you a question. If we do the same thing here, if we're going to double the value for Q, and we're going to double the value for R, what will happen to the potential energy?
Double Q and double R. Oh yeah, there was nothing.
No change.
Honestly.
Now, those are kinds of things that come up on the MCAT. Other things come up too, but that's one of them. They like proportionalities a lot.
Yeah.
Okay. So what we're going to look at now is we're going to take a look at a single charge. And what we'll do here is we'll make it a positive charge. And that charge will be next to another charge like this. And this is called a test charge. And the thing about a test charge, it's going to be small and it's going to be positive. That's the rules for a test charge. Now, it turns out that there's an equation that says force is going to be equal to E times Q. Now we know that force F, we know Q is the coulombs of this charge here. Okay, but what's gonna also happen is that this right over here is gonna be called the electric field. And this is something we invented to make it easier to do calculations and to visualize what's going on. So if we define the electric field in another way, we could say the electric field is going to be the force over the charge. So the charge is this charge. And the force is going to be something that looks like this, just what we talked about. That's Coulomb's force, Coulombic force. And the strength of the electric field is going to be defined by this charge right over here. So that electric field is going to be in the same direction as this force here because they have the same sign. And we know that positive and positive repel. So this is the force on the charge, and then this over here is going to be the electric field. And it's going to be radiating outward from the positive charge, just like that, because this is the definition. And we know if we stick a test charge, which is positive, next to a positive charge, then the force is going to be away from that positive charge. Does that make any sense?
Mhm.
Okay. Now, if we have a negative charge like this, make it blue, then the electric field is going to be going in this direction because there will be an attractive force. And what's important here is that this is one of the definitions for an electric field. So the electric field may be thought of as the force that will be placed on a test charge here when placed next to a larger charge when it's positive or when it's negative. When it's positive, the force will be this way. When it's negative, the force will be that way. So when we have a positive charge, we're looking at the electric field doing this. Oh, I messed up. I'm thinking about where I'm going, not where I am. So that is what happens with the positive charge. And then with a negative charge, what's going to happen is we're going to get that. Now, you may be wondering what would happen if we stuck these together, like next to each other. So if we do that, the lines are going to represent the forces on a test charge. That's what these electric fields are, the forces on a test charge. And on this far end, it's easy to figure out what's going on because what's going to happen is it's going to be pretty much the same. And I got to get my colors right. I want to use purple so I'm consistent. You see, it's pretty much the same. And over here, it's pretty much like that. It's in the middle where it gets different. And that's because in the middle, we've got both of these here. So what happens in the middle, it does this.
Mhm.
So that's what you get when you put the two together. So if we put a test charge, a small positive charge here, it would follow this path. That's what the electric field line is, that path it follows. Now, what would happen if we did something like this? Suppose we put a negative here and a negative here. We could pretty much guess that's what's going to happen is we're going to get the same here, like that. And then we're going to get the same here, like that. But then what's going to happen in the middle is these lines are going to avoid each other because negative isn't going to work the way positive does. So let me see if I'm going to do this right, because I'm getting confused now as to what's going to happen. Oh yeah, what's going to happen is this one is going to go in like, I'm gonna get stuck on this. It's been a while since I did it, so I'm just gonna cheat and do this, and I'll figure out what's gonna happen on the other. Okay, so on the positive, I can do this easily. What's gonna happen here is it's gonna be going like this, like this, like this, and then it's going to avoid going into the positive. So that's what we're gonna get. Because when it's positive, the electric field line won't go in there because this is the path of a positively charged test charge. Mm-hmm. Now, because I got stuck on this one, I'm going to have you help me. What's going to happen here? By the way, I just figured it out. We're going to have you tell me.
Well, I don't want to touch each other, so I feel like we would go this way.
Oh, let me see. I wasn't looking. Yes, you got it. Oh, you got it. Yes. You are an expert. That's right. It's going to go like that. Exactly. It's kind of the symmetric opposite of the one we did before. Yeah, that's it. Good. Very, very good. Okay. So the thing we don't have is we don't have a formula for what E is going to be. So that's what we're going to do now. It turns out that E is going to equal KQ over R squared. KQ over R squared is going to be the value for E. Is this an inverse square law?
Yes.
It sure is. Now, as far as this equation goes, there's something we need to talk about which is related to E, and that is that we can define E in this context, or, and we haven't talked about this yet, we can define it delta V over R, which is the distance. So what I'm going to do is I'm going to create a uniform electric field. Now these guys here are not uniform. When you have parallel electric field lines, you're uniform. When you don't, you're non-uniform. So these are non-uniform. But if we go ahead and we create a plate over here, and we create a metal plate over here, and we hook this up to a battery like this, and the larger end is the positive, and the smaller end is the negative. And so this plate becomes positive, and this plate becomes negative. But instead of being one charge, you got a whole bunch of charges. Now, when we had just one charge, we had something like this right over here. Mm-hmm. But when we got a bunch of charges, these lines don't curve except at the ends of the plate, so that we basically end up with electric field lines going straight across. And what's going to happen over here is there's something called, let's not use purple, let's use green. What am I going to use green for? Magnetic fields. I'm going to use electric fields purple. I need another color, blue. Okay, so voltage. Voltage is going to be the energy per unit charge. Now, what this means is that if we have a wire and there's an electron in that wire, each electron has so much energy per unit charge. Now, what's the charge of an electron? The charge of an electron is negative 1.6 times 10 to the minus 19 coulombs. So for every 1.6 times 10 to the minus 19 coulombs, each electron has a certain amount of energy that you can use to do work. And that's the voltage. Now, when you have a dryer, they use 240 volts because a dryer needs a lot of energy. But when you have something simple, like a clock, then you use 120 volts because you don't need as much energy. So what voltage is the energy per unit charge, or we could call this in terms of units, the number of joules per coulomb. Now, an electric field can be defined not only in terms of the force per unit charge, the force per test charge, but also the change in voltage over the distance. Now, this is another definition for E. E, it's not only equal to force over the test charge, it's also equal to negative V over the distance. Now, the negative you don't have to worry about because it just tells you the direction. So don't worry about the negative, just like we didn't worry about it in Coulomb's law. But what we can say is that in a parallel plate capacitor, we're going to have sections of this like this. They're like little plates here, and they're all going to have the same voltage. So when we measure that voltage here, we get delta V. That's the difference from one spot to the other in energy. And we can also measure this distance here in terms of R, and we can divide them, and that will give us delta V over R. And that is another definition of the electric field. And when the electric field is uniform, it's much easier to look at it and see what's going on. Did that make any sense?
Yeah, it did.
It's a little weird though, right?
Yeah.
Okay, so did you want to ask a question? Because it's not as intuitive.
I feel like I just need to memorize.
Yeah, that's what you need to do.
Yeah.
That's true. You don't need to really have a super grasp on it. You just need to know that. Okay. So you can plug it in when you see it.
Mm-hmm.
Okay. However, one of the cool things about this is that you'll notice that the electric field lines, purple, and these sections, which are called equipotential surfaces, that means the voltage, equipotential surfaces are all the same. They all have the same voltage. They're all perpendicular. See that? Look, they're all perpendicular. So a question would be, is that going to be true, that they're all going to be perpendicular when this is not going to be uniform? And the answer is yes. So it tells us something important here. I didn't actually draw this out as fully as I could have to demonstrate this, but I will still use this. That is an equipotential surface. It's a surface if you make it a sphere. And this is going to be uniform voltage. So it works that way always. It's always going to be perpendicular here and all over there. And what's going to happen is that voltage is going to come out like that, and there'll be a voltage like that as well. And those will all be the same. Okay. They're going to be perpendicular here as well. Now, you might wonder, what would this look like if we turned it on its side? Like, we're looking at this from the top, but I wonder what this would look like if we looked at it from the side. Like, let's say we were standing here and we were just looking at it, not from the top, but from the side. What would we end up with? And I'm going to draw it right on top of this. But what happens is it goes to infinity here, and it goes to infinity here. But what will end up happening is it's going to be something like this. Over here, it's going to be way up like that to infinity, and then over here, it's going to be way down like that to infinity. Now, that's probably something you might not see on the MCAT, but that's the way it works. Because what's happening is, as you get closer and closer to this, this gets larger and larger, the voltage does. So we're talking here about how the voltage is going to change with distance. Okay, so for this, not so important, but I just felt like showing you how that works. What you're wondering about, though, is we have an equation already for the electric field. We have the one that we talked about like this.
Mhm.
And I should have probably told you this is for a point charge. So this equation over here doesn't work when we have something like this, because that's not a point charge, that's different. So we wouldn't be able to use that equation here, but we would be able to use this equation, and we would be able to use this equation. But the other one is just for a point charge. So what happens is you have E is equal to KQ, that's wrong, KQ over R squared, and this is a vector. And then what you have is you have V is equal to KQ over R. And this is a scalar. So a vector has magnitude and direction. And a scalar just has magnitude. So what this means is that when we're looking at the electric field, it's arrows. You see how it's arrows? Those are vectors. But when we're looking at voltage, it's not an arrow. That's a scalar. Does that make sense?
Mhm.
Now, electric field should be a vector because it's the direction it pushes the test charge, or the direction the voltage changes them. And the voltage should be a scalar because it's just a quantity of energy, not a direction. Okay. So has this been pretty exciting so far?
Super.
Absolutely. I can tell. Okay. So what we're going to do now is we're going to come over here and look at this. What happened? And we have this. Have you ever heard of a parallel plate capacitor?
Parallel plate capacitor.
Well, these are parallel plates. And what a capacitor does, a capacitor is going to store charge. Capacitor is going to store charge. And the way it stores charge is, it's going to have a certain number of coulombs, the unit of charge, and then that's going to be divided by volts. So it's the amount of charge that you can store for a given voltage. And that's going to be big C. Now here's the problem. Somebody decided to use big C for capacitance and big C for coulombs. So that's the reason I didn't put a C here, a big C, because it would have been confusing. But yeah, you should be aware that this is a big C and that's a big C, and you know, that's it. That's the way they did it. Anyway, if you have a capacitor, you want to store charge. And the more charge you can store, the better for the fewer amount of volts. So what happens is that one of the designs of a capacitor is a parallel plate capacitor. And it consists of these two parallel plates. We hook it up to a battery, and then what it does is it loads charge onto the plates. Now, while we're talking about this, when it loads the charge onto the plates, there's something called conventional current. And conventional current is a little bit confusing because we normally think of electrons as the conductors of current. Certainly, we know that that's the case. But when they worked on physics before they knew what was the current carrying substance, they basically assumed that it had a positive charge rather than a negative charge. And because of that, conventional current is going to consist of positive charge carriers. Positive charge carriers. So that would mean that the conventional current would go this way. Now we know that the electrons are going this way, but in physics, we are typically going to work with conventional current. So that's the way it works. And so what will happen is these positively charged carriers, which are non-existent in this case, imaginary, will load up on this plate, and then this will become positive, this will become negative. And if we remove the battery, there's no connection between the two plates. So what will happen is it will store charge. And that will be the design of a parallel plate capacitor. Now, when you have an electronic circuit, you want to store charge, this is the way to do it. And there's some interesting properties. We already know that the electric field in this design is going to be uniform and that the voltage is going to run this way. So we have that. But we also have an equation over here for a parallel plate capacitor. These are my cheat sheets here. And here's how that looks. For a parallel plate capacitor, we're going to have the capacitance is going to equal a constant right over here, which is called the dielectric constant. And then there's going to be another constant called the permittivity of free space, which you don't need to worry about. It's just one of those constants. A is the area of one plate, and D is the separation between the plates. So this is A over here. These are the two plates, and then this is going to be D. And that gives you the amount of charge, that's the coulombs, that can be stored for a given voltage. Now, there's a couple things we need to talk about. For instance, if we double the area, what will happen to the capacitance?
The increase.
That's true, but how much? If we double it. What?
It's gonna double.
Yeah, sure. You're a little timid, but yes, we know, we stick it to it, right? It's easy. Everybody can do it. Okay. What happens if we double the distance?
Gonna go half.
It'll half, right? That's right. Okay. So what we need to do is to talk just briefly about this, the dielectric constant. When they create a parallel plate capacitor, they normally put a material in the center here, and they call this a dielectric. And it's a material which is going to form dipoles like this. And when it forms a dipole, it's going to increase the capacitance. So this is a constant here, which shows us by how much we can increase the capacitance if we use a dielectric. And it's called the dielectric constant. And the reason why it works the way it does is the dielectrics lower the energy of this parallel plate capacitor, and that allows it to store more charge. Now, I'm just wondering, do you think that a charged up parallel plate capacitor has potential energy?
Yeah.
Yeah, it does, because if we were to hook these wires here together to some circuit element, then what would happen is there would be a flow of current. So it turns out it does have potential energy, and we can define that as 1/2 CD squared, where C is the capacitance over here, and V is the voltage between the two plates. So you can take that energy and you can release it. Now, a capacitor can be charged up and it can be discharged. So what happens is, if we're going to charge it up, we're going to hook the wires onto it. What will happen is the charge is going to build up, and this will occur with time. And as it builds up, what's going to happen is it's going to reach a limit, and that's the maximum charge that it can store. So that's going to be when it charges up. Now, when we look at the capacitance, we said that capacitance is going to be equal to Q over V, like this. When we measure this, we're talking about the maximum here for a given voltage. So that's how that works. Okay. Now I'm slightly distracted because someone is cooking in the kitchen and she just burned something really bad and I can smell it. But anyway.
As long as it doesn't burn the house down, you're good.
It's not really burned though. But anyway, it's like, yeah, it's like really, really burned. Okay, I'm glad the fire alarm didn't go off.
Yeah, I should crack a window.
Yeah, something, yeah. Okay, so if we take this right over here, this is Q, and this is time. And then this over here is going to be discharge. So now it would start up here and then it would go down to 0. So that's how it looks when it's going to be charging and how it's going to be look when it's discharging. Now, because this shape here takes up more room than they would like, they've come up with a design of these where nothing really changes. All the equations are the same, but it doesn't take up as much room. And what they did was they took the parallel plate capacitor and they curled it into a cylinder. So what happens with that is they took these two plates like this, and they basically did this to them, like from the top.
Mhm.
And so when you look on circuit boards, those little cylinders, those are actually capacitors. But on the MCAT, they've actually talked about this. And they'll give you the area, and they'll give you everything just like they did over here. And you deal with it the same way. Even though the areas aren't exactly the same, it works fine. So you see something like that, you treat it as if it's a parallel plate capacitor.
That be something like, I don't know if I'm pretty sure it's called concentric objects. Would that have to be applied to that?
Say again?
Like the concentric objects? I read something that the force goes around circles. I don't know.
Something about concentric is what we have. This is concentric. Concentric means like circles around circles. Was it about capacity?
Yeah, I was like how the charge wraps around it or something.
Well, yes, the charge does. I mean, what happens is if this is the positive plate, it'll do this.
Mm-hmm.
And then if this is the negative plate, it will do this. And then the electric field lines, if we kind of make it larger, the electric field lines from positive to negative will do that. Now, if you were a scientist, you would say that the capacitance isn't exactly the same as this because these are not going to be a uniform electric field. And so there must be some difference. And there is. But on the MCAT, it doesn't matter.
Okay.
But that's what they've done. And they've done it just to save space because this takes up too much room on the circuit board. Okay. Okay. There's some things I'm skipping because they're not in the MCAT. I know you feel that's terrible. You want to know everything, but
it's okay.
We'll make room for that.
I'll survive.
You'll survive. Okay. Moving current. No, not current. Charge. Moving charge is current. Now, usually that's electrons, but it could be an imaginary positive charge carrier, conventional current, but it could be a sodium ion or a potassium ion, right? Or a chloride ion, let's say it goes that way. All of those are current. And the symbol that they use for current is going to be I. And what happens with I is equal to the number of, well, let me do it this way, coulombs per second, but instead, because of that C is confusing, we'll say it's Q over T, okay? Which is the coulombs over seconds. And this is called an amp. So the number of coulombs that pass a point per second is the current, given the symbol I, with the unit amp. Okay. Now, there is something called Ohm's law.
Yeah.
And everybody that takes physics 2 knows Ohm's law. V is equal to I R.
Just think beer.
Veer, yeah, veer. You have nothing to veer from Ohm's law.
Good one.
So we know what I is, we know what V is. And R, you probably know, is going to be resistance.
Mhm.
Now, what happens is if you have a battery, and this is 10 volts, and here you have something that is known as a resistor, what will happen is in the resistor, the voltage will drop. And if all you have is one resistor, the drop in that voltage is going to be whatever is in the battery. That's going to be 10 volts. If you have more resistors, it'll be across those resistors in various ways. But this equation will apply. So what will happen is that if the resistance here is going to be 2, and the unit is going to be an ohm, so this is going to be 2, and there's our symbol there. So that is an ohm, the unit of resistance. Then we can calculate what the current is going to be in this wire. So what we have here is we have a voltage of 10, and we have a resistance of 2. So that means that the current is going to be 5, and that's going to be amps, because that's the unit of current. So that's one way of using Ohm's law. Does that make sense?
Yep.
Now, I mentioned that you could have more than one resistor. So what happens is, if you have 2 resistors, this is going to be R1 and R2, then if the current is going to have to go through both of them, if it has to go through both of them, then they're going to be in series. So current must go through both. When that's the case, it's going to be a series circuit. And when it's a series circuit, you probably know that there's something called the equivalent resistance. And the equivalent resistance is going to be R1 plus R2.
Yeah.
Very simple. So you would just add them, and then you could calculate what the current would be. On the other hand, you could have a parallel resistance. The parallel resistance means that the current does not have to go through both. In fact, it can't really go through both unless it turns around. So what happens is at this point, it'll go that way. And then at this point, it'll go that way. So when it's got 2 ways to go, then that's going to be parallel. And if we go ahead and, oh, I'm just curious what you're saying. I'll, read that later. Okay. And when they go in both directions, this over here, we'll call this our resistance 1, and we'll call this over here resistance 2. And then what happens is this will be 1 over R equivalent, and then see, it's like a reciprocal. This is 1 over R1, and then this is 1 over R2. And you would plug that in, and then you could solve for I. So those are the basic forms that Ohm's law can take on when you've got more than one resistor. But the form is basically this. V is equal to IR. Now, Ohm's law is the biggie, but there's also a little law here, and it has to do with something that's not resistance, it's called resistivity. And it's a measure for a material. So here's how that works. It says that the resistance is equal to the resistivity times L over A. So this is resistivity, and it's a constant for a material. Now, essentially what this formula is saying is that if we double the length, then the resistance is going to double, right?
Mhm.
And if we double the area, the resistance is going to half, like that.
Yes.
That's what we've been doing all the time.
Mhm.
Now, different materials have different resistivity, and you would just plug that in. So that's pretty much how that works. And all this stuff you don't really need to worry about.
And the little p looking thing, that's just the constant, like you said. So it doesn't.
Yeah, that's the resistivity here. That guy. Yeah, that's actually, let me use a different color. That's a rho. By the way, the MCAT tends not to use rhos because people confuse them they're now on computer screens. So they use a different letter. But like for density, that's the symbol for density. But in the MCAT, because people confuse it, it's hard to read, then they use D.
Yeah, that's true.
So, I don't really know what they use for resistivity, but because it doesn't appear that much. Okay, so we've got to a point where it's time to look at power. Now, if you think about what power is a rate. And anything that's a rate is going to have a number here, and it's going to have time right over here. That's what a rate is. Like velocity.
Mhm.
Velocity is a rate. So anything, this would be displacement over time. So what happens is the symbol for power is P, and what we have for power, we're usually going to use joules or kilojoules. It's going to be joules per second, and that's going to be power. Now, in terms of electrical circuits, though, we can define power in 3 ways. We can say